All right, good morning, everyone. Welcome to the event. This is the Atlas stage. I'm Travis Fraser. I'm the stage manager for Atlas, so if there's anything you need over this weekend, please come to me. And I'd like to introduce our first guest. It's Jiang Gao with Microsoft. So come on up, Jiang.
Hi, good morning. I'm Jiang Gao from Microsoft Research. I'm very glad to have this opportunity to present some of our recent work. I picked a few projects around the topic called agentic modeling. As I show you in the title of the talk, right? This, can you see this? Okay. Agentic modeling by internalization agent harness. So before I go into details, I want to give some definition regarding the three terminologies I used in the title: agentic modeling, internalization, and agent harness. And agentic modeling actually aims to transfer large-scale language models into an autonomous agent capability of performing complex tasks by interacting with the environment. We all know that portraying a large-scale language model is merely a talker. It seems that the model knows everything, but it's really difficult if you ask the model to do something for you. So agentic modeling is the process where we want to turn this talker to a doer. And the so-called agent harness, I think everyone familiar with the terminology. Okay? Usually, because the large language model cannot do a lot of things, it's just a talker. So in order to make the language model to perform some real-world task, you need to couple it with the large language model sort of an agent harness. So when we talk about AI agents, usually it's the combination of the language model, probably multiple language models, and the agent harness. In some sense, the harness is a bunch of code. It can handle a lot of things that the current language model cannot handle well. Internalization refers to a process of distilling agentic capabilities from the harness to language model. What are these capabilities? A great example is the memory or context management to use and planning. Typically, this is achieved by mid-training and post-training large language models through supervised learning or reinforced learning. Okay. This figure shows some key components that are needed for agentic modeling. There are three of them. I use different colors. In the left-hand side, this part is the agent. For example, we assume that our lab is not building a new large language model because it's so resource intensive. Microsoft has a dedicated team called MAI. They are responsible for building in-house large-scale language models such as MAI. I think they released dozens of models recently. It helps Microsoft stocks. Okay. Again, we have deals, contracts with other companies such as OpenAI. They provide us their frontier models. And we have Azure Foundry, which can host hundreds to thousands of open source language models. Yeah. But the focus of the lab actually is to develop enabling technologies to help develop the agent harness. Agent harness can be viewed as hard-coded modules and the layers. They're not models by themselves, but they are modules. Most of them are hard-coded. These layers can do things that the current language model cannot do well. For example, the information layer consists of the memory and the context management, and contains a lot of tools and the skills for the language model to call. And the execution layer consists of a prompt builder, action parser, task decomposition modules, and some error recovering mechanisms. And most importantly, the feedback layer, which helps the system to collect all the trajectories generated by the agents. And these trajectories can be used to refine the underlying model, the LLM, by post-training. This actually is the key of the agentic modeling, okay? That's the first part. Second part is the environment. In some sense, the environment, sometimes people call this reinforcement learning environment, or RLEs, okay, where the AI agents can interact with the external world to perform tasks while generating trajectories. And the last component is the yellow one. It's the trainer. It's a model trainer, where the generated trajectories are used to improve large language models' agentic capabilities by post-training and mid-training. Some of the, for example, most important training methods are reinforced learning and its variations, such as policy distillation, reverse KL divergence algorithms. Actually, here, for the trainer, the cost efficiency is the key. So it's not only that we require the model to be served in a cost-effective way. More importantly, we hope that the model training is very sample efficient, meaning that probably we don't need a lot of samples to train the model. Putting together, we witness a new paradigm of AI modeling, where harness is like the training data to agentic modeling, just like the internet data to model per training, right? As AI industry and the community are building many AI agents and harness almost every day, then we actually witness an emergence of a new data flywheel, where distillating agent capabilities from harness leads to AI models that are more capable of doing things, and which these models can help us build even better AI agents that can generate more sophisticated trajectory data and by solving more sophisticated tasks. And again, this process continues as we advance both the harness and the models. Okay? So many of the ongoing AI research projects at the MSR can be grouped into these three categories, as I outlined here. For example, the modeling technology, as shown in the green box, to facilitate harness engineering, such as memory management and test time learning, and the environment service, as shown in the blue box, and to host in parallel many reinforced learning environments where agents perform tasks and generate trajectories. And actually, this is the source of the training data for agentic modeling. And the yellow box, the trainer. So, in workflows, I will present for each group an ongoing research project we recently released to the public, or we're about to release it. On the environment side, I will present our chart, which is an open source agentic model framework for research. As for agent harness, I will describe a new test-time learning framework called Evolve Lab, which allows large-scale language models to accumulate, reuse, and involve knowledge across a sequence of tasks. And on the model trainer, I will present GFlow.io, which is a new reinforced learning method, which I really hope can provide an alternative to the dominating RL methods such as GRP or PPO, because this new method unlock the great diversity and turns out to be a more cost-effective training method. Okay. This is the overall, it's a summary, one slide summary of the Orchard project. And I believe the paper and the code and data will be released sometime next week. We know that despite the rapid progress in AI aging, the open research on agentic modeling remains constrained by infrastructure gaps. Early days when we are doing this pre-training, as long as you have access to internet, there's no lack of training data. You can grab the training data from the web. But agentic modeling is different. You need an environment to run hundreds of thousands of agents simultaneously so that they can generate a lot of trajectory data. And then you can use this trajectory data to train your model. So it's not there yet. In the research community, people have been focusing on infrastructure mainly designed to improve the harness itself, but not the environment that can host different agents to run in parallel. So to narrow the gap, we present Orchard, which is an open source ecosystem for scalable agentic modeling. At the core of the Orchard is a thin Kubernetes native environment service that provide a reusable primitives of sandbox lifecycle environment. It's called Orchard environment. In some sense, the Orchard environment is like an operating system runtime for AI agents. It acts as an orchestration and a virtualization layer that manages the container images inside the sandbox that expose a clean interface for the AI agents to run. Intuitively speaking, what this does is provide the environment. It's just like the organizer of this workshop, organizer this conference, right? The operating system in this context is like this building, okay? It provides all the electricity facilities to us to host a lot of workshops. If we view each workshop as an agent, then the organizer of this conference did a great job to put each workshop in a particular room. This is like a reinforcement learning environment, mini reinforcement environment or pod in this context. And after all these workshops, the organizer will, again, collect all the results of this workshop and share the results with us. In some sense, the Orchard environment is the organizer of this the whole conference. Okay? Then in order to demonstrate the effectiveness of this environment, we build 3 agentic modeling recipes on top of that as a demonstration. Okay? First is Orchard environment. First is Orchard Swing. This is target to the software engineering agent. What we did is we distilled about 100,000 trajectories from the models. And then it's interestingly, we see that we got very good results, 73%. If you know this benchmark pretty well, this we bench verified. This result already surpassed a lot of open source models, regardless of the small size of the model. Then we also take 2 other examples. Which is the Orchard GUI. GUI is for navigation. The other is Crawl. Crawl is for personal assistant. Now, this is I want to give a quick update of this project. It's test-time learning with involving libraries. Memory is important, but typically we view a memory as a storage of raw experience. But this experience is not learning. This experience, very quickly you will say, oh, I collect a lot of experience previously. I have no idea how to use this experience to solve new tasks. But human learning is different. I never recall all the details of my previous experience. I only remember what matters. right? The failures I try to avoid, the new skills I learned once, and hopefully I can apply it multiple times in the future. So this algorithm is developed to simulate the human learning. Now, the last project I want to give an overview is GFlow-IL. The difference between this and the traditional approach, like the GRPO, is that in this reinforcement learning setting, we define policy learning as distribution matching rather than reward maximization. The key difference is that now, using this algorithm, we can sample trajectories, sample solutions proportional to the reward, proportion to the reward they got assigned. Okay. Yeah, I have to stop here. If you have any questions, feel free to reach out to me in an offline manner. Thank you. Thank you.
Thank you, Jiang. Appreciate that. All right, next up, we have Sanya Fidler with NVIDIA.
Yeah, hi, I'm Sanya. I actually no longer NVIDIA. I just announced it yesterday, recently left. But NVIDIA has been really kind and actually allowed me to take my slide deck with me, or at least quite a lot of the material. So I'll be talking about the NVIDIA work today. But today I'm a civilian at University of Toronto, and I'll let you speculate about my next steps. All right, so I'm not really going to talk about agentic AI today, but I'm going to talk about world models, which is really something very exciting to me, really for the last 6 years. But now this technology is maturing, is around the corner. All right, so we've been working on physical AI for quite a few years, and the world has been working on robots for decades, right? But if you look at kind of this evolution of AI, ChatGPT 2022, kind of the entire world knew about AI. It was the first time that really reached the masses. My mom knew about ChatGPT, right? Right now, we are in the era of agentic AI. Everyone is using agents. I don't need to explain what it is. I cannot imagine my life, actually, without using agents. And the next breakpoint that is coming, perhaps in the next decade, maybe more, depending on the kind of robot we're going to looking for, is physical AI, where all this intelligence comes to the edge, comes to the robots, in many different roles, in many different industries. All right, so at NVIDIA, we were, at least my group was more focused on one particular robot, that was autonomous driving robots. Today, we're going to kind of use that as an example. But obviously, there's many robots, especially general robotics is kind of the hot field that's upcoming, and it's the robot that kind of a lot of echo, supposed to do many different tasks. Okay, so the evolution of kind of the software to deploy on smart robots, for example, a car, kind of went through different generations. From very simple AI or a simple vision to more hard coding rules around how could I be driving around, to machine learning in every single steps, both in perception, but then also prediction and planning and how I'm going to actually drive the car. To most recently end-to-end systems where I'm just taking sensor data and outcomes, basically a planning trajectory that drives the robot, drives the car, to perhaps the new generation that's coming, which is leveraging this big foundation model pre-trained on massive amount of data that come with this vast knowledge about how the world works around all the corner cases that is so hard to collect in the real world, and also know how to reason. So people really think kind of this foundation models are a game changer to really kind of that last mile to solve the corner case in robotics or in AV as a first complex example. All right, today I'm not really going to talk about so much about the software that goes on the robot, but about the infrastructure, particularly simulation, right? So if you think about LLMs, during development, people train a lot of different models, and you need to somehow evaluate how good they are, which means sampling from the model, get some text, and have some way of evaluating how good it is. Sometimes even interact with a human, right, if you want to measure conversation. So something like that in robotics actually needs to be deployed on a real robot in closed loop, right? Meaning, I have a software, the brain of the robot, I deploy it on a real robot, this robot starts performing some tasks. Here I have some video from Skilled AI that I pulled from the internet. Real robot doing pick and place, running this policy, which we develop in their environment. And then, the human is kind of observing how good this robot is doing, right? An alternative is to actually have a robot do this in an entirely virtual world, right, on the cloud. So it's a virtual robot in a digital twin, also doing pick and place, right? And we can also evaluate how this virtual robot is doing, and that can also give us a really good signal about which policy that we develop is actually better, right? And we can also train that way much more scalably. So if we look on the left side, the development is kind of bounded by deploying on the robot, which runs with physical time. We cannot, in the real world, we cannot run faster than the physical time, right? So if we want to scale and evaluate many, many different scenarios, we need to buy many, many different robots. On the cloud, on the other hand, we're bounded by compute time. Computers are getting better and better. We can actually run faster than real time, and we just scale across GPUs, right, instead of robots. So it's a much, much, much more scalable pipeline. So simulation is really kind of foundational infrastructure for robotics. I really don't think you can develop robotics without really, really good simulation. Let me skip this slide. And talking about simulation, it has kind of gone through different stages, right? So, traditionally this was done by graphics. Artists would carve out, create 3D assets, write behavior models, write all the ray tracing equations, and then you would get out a particular scenario. It kind of worked, but at the same time, it was so time-consuming. If I wanted to test my car at some street in San Francisco, that goes 1 or 2 months of actually artist time to create that digital twin. Then around 2020, a new technology came along called neural for Gaussian splats that completely changed the game. And the game changer was that now you can go from a recording, from a real-world recording that you capture on a real robot, to a simulation environment with some restrictions because it was all done by reconstruction. So it was kind of limited with what you actually saw in that recording. But it was a game changer. Suddenly, the content problem was solved. You could go from real-world capture to a simulation environment, deploy a new version of your software, and make new closed-loop rollouts and actually test new policies in these environments. How did this work? It was all reconstruction-based. You have your capture. You get your surface reconstruction for collision checking. And then you're inferring Gaussian splats with these kind of little appearance blobs in space that tell you how to render different viewpoints. Complete game changer at NVIDIA. We were doing 2 million simulations per day testing autonomous driving software. All right, so is that enough, or what's coming next? Like I said, there was a lot of limitations of how you reconstruct the environment, what kind of environment you can actually handle. Plus, at the same time, it's also bounded by what you have recorded. And we talked about the robotics is going to hit the long tail, which is stuff that it's so hard to see. And you actually need to test and train in those environments. So it's all about imagining those hard cases as well. And this is where world models or generative world models come in, right? This is AI purely trained on data. It's completely data-driven. There's no more human crafting content. So the limit is the data, and we have learning LLMs. That's basically the way to go. And suddenly you can hallucinate new scenarios. You can write whatever new hard edge case you imagine in very kind of hard dynamic scenarios. Lots of progress on this front, right? Especially in the last year. Now we can generate really crazy hard scenarios. Kind of like hard weather. No one got hurt in that video. It was completely generated accident. It's just really kind of those cases where you want to test the software. Here we can even change the viewpoint, which is similar to basically changing embodiment, going from lower car, sports car, to a truck. Super important, so you can actually test across different vehicles. And the last really important thing that's very easy to do with generative models, but a little harder with reconstruction tech, is editing. Just text prompt, and suddenly you can edit scenario in different ways. All right, there's a specific architecture that I have in mind when I talk about world models today, and it's interactive. So it's not just I'm getting text, I'm getting out a video, 5 seconds of video. There's a user or a robotic software in the loop. Here, our favorite human at NVIDIA was actually our first user. As soon as we developed the model, we went to his office, and he was the one trying it with a real steering wheel. So in this case, it was a user driving, and every single frame that you saw was completely generated by the world model. And that's what I mean by world model in this presentation, and that's why being interactive. There's a robot or a human in the loop. And that model that we developed was called OmniDreams, and the bonus is that it runs real time. Does simulation interval real time? Not necessarily. It just needs to have really high throughput, but real time is a great bonus. All right, so I'll just do a quick glance of how we actually developed this. Today, obviously in the future, this is going to be a lot maybe simplified and so on. But right now, everyone starts with a base model. This is a pre-trained video generation model, typically based on diffusion. So you have a few, like a noisy frames, and you denoise them into, a few seconds of video. This is what I mean by bidirectional attention model. Now we typically do domain post-training. This was pre-trained, typically, on vast amount of publicly available internet data. Now you need to go to a specific robotic domain, for example, AV, and you need to post-train such suddenly I can start generating stuff that happens on the road, right? And not just stuff that happens on the road, stuff that is captured by a robot, which is typically more than just one single camera. It can be many different cameras. Then we need to train this architecture, right? We said we need to make it interactive. So we actually changed to have this causal architecture, right? So it needs to generate frame by frame, or at least like short snippets of video at a time with action in the loop. We need to make it efficient. Typically in this diffusion models, you do many steps of distillation, which makes it slow, but you need to distill it into just a few steps of distillation so you can actually be much faster. And then you do all the tricks in the book to actually have a real-time implementation. And this is Flash Dreams. We released it, and you can plug it on different architectures of world models. And then the world model comes out. So here you have someone driving. On the right side is a steering wheel that's being operated. Every single frame here is not the real world. It's completely generated by the world model. And here we have very simple physics. It's just physics on the ground. So we make sure that the car stays always on the ground, goes over speed bumps, but you can actually go through a restaurant no problem. So we didn't have collision checking on more complex part of the scene than the road. All right, I wanted to show this because I think it's really showing the trajectory of where this is going. March 2025, we were generating 5-second clips, 5 minutes or so. 5 seconds, 5 minutes of GPU time. Okay, it was clearly not practical. On the right side, March 2026, that was fast forward by 1 year, real time, interactive. Okay, so this is how fast this technology is evolving. This is why I mean it's around the corner. At CVPR, which was basically 2 months later, this was June, we even made it work on RTX 5090, which is basically a consumer-grade GPU, which is awesome. It's literally a game engine that you can have in a backpack. Just some example results. Everything here you see is completely generated, and it's just giving it a text prompt or a first frame, and you get a desired scene, which is much more complex. There's no way that this can be done by graphics engine. It's just too much, or too many different phenomena going on. And it's very hard for the construction tech to actually generate this as well. And this is basically showing what you need to do in the end, which is generate multiple different sensors that you have on the robot. This is pretty cool, because here we're actually editing the same environments. We can change the weather, the lighting conditions, and that little green trajectory that you see, that's actually the robot's policy driving in this world. I was actually super excited about this result because we plugged it in the production policy and it was driving in this world. It's confusing the simulated world with the real world, which is basically means that the quality bar is at the level that you actually need. Yeah, and I asked my guys to generate some cool examples. And this is basically just saying that you still capture that internet knowledge. So even though NVIDIA has never captured an elephant on the road, you can actually generate it, which is proving the point on that long tail. Yeah, and then maybe just kind of end here with the interactive demo. Just so that you see it actually runs real time. On the left side is the person really driving it. Every single frame is generated. On the right side, you see that wheel rotating. That's actually the robotic software operating that wheel and driving in this 3-camera world model. So thank you very much. I'll stop here.
All right, thank you, Sonia. I appreciate that. Next up, we have Giambattista Padascandoio, or GB, with OpenAI.
Okay, so why are these slides old? I'm basically going to show you some of the earliest presentations that we had internally at OpenAI when we started to work on reasoning. So this talk is not about the future. The slides are also really ugly because these were never meant to be presented in any occasion like this one. So these are just slides for our teams from a long time ago. So think about it as more as a time traveling and seeing what it was like to work on reasoning a while ago. Okay, so first, what is reasoning? Again, these are the old slides. So maybe one way to think about it is to say there's a big space of problems of all kinds of subjects, and then you could think of this colorful wheel as all of the different things you could be thinking about. So there's AI and math and physics and biology. And then let's say the central radial axis is difficulty. So as you move the angle, you change the subject. As you move away from the center, you change the difficulty. And so the main thing we were having at the time is that we were pre-training all of these models, like GPT 2 and 3 and 4. And then the circle of problems they could solve would expand from the middle. And they would kind of cover all of the subjects a little bit and solve slightly harder and harder problems as we went. But then the main issue is, when were we going to solve the really hard problems? And then if you think about some of the human experts in different subjects, for example, Andrew Wiles, who solved Fermat's theorem, well, this guy thought about this problem for 7 years. But it's not like he could solve everything at the same time that took 7 years to solve. He could solve one problem that took 7 years. And most of the hard problems are like that. And so in some way, there was something about this process of just pre-training models to be better at general knowledge that seemed unlikely to eventually expand the circle all the way to cover all the hardest problems. So what do we do as humans? We think, we reason. So can we give models the same capabilities? Okay, so now we're going to do something a little fancy. We're going to move this wheel in 3D. So we're going to tilt it this way. So pay attention, because it's only going to happen once. Okay, so now it's on the side. And then we're going to move it to the side of the screen. And now we can add the third axis, which didn't exist before, which is time, so thinking time. And then the question becomes, how do we expand these cylinders that don't really cover anything else given more time? Maybe it might look a bit ridiculous today, but there was a time where you would give a model more time to think, and it would give you the exact same answer. Because after a few milliseconds, you would get the answer, and it would not know what to do with the extra time. And so thinking was this idea of, well, can we expand this cone over time? And not all at once. Again, you have to pick one little thing to focus on and then discover that. And so there were lots of practical problems. I'm not going to talk about almost any of them. But the thing to also think about is, well, how long is this reasoning? Because again, Andrew Wiles thought about this problem for 7 years. And so in terms of our models, well, at the time, they only had a context of a few thousand tokens, maybe 8,000 tokens. And then what can you do with 8,000 tokens? Well, at most, a few seconds of reasoning. And so there were lots of interesting questions of, even if we get them to reason, then how is it going to happen? Okay. Now, the other issue was we didn't know what reasoning would use as a substrate. There were lots of different ways you could spend test time compute, right? You could do you can have a recurrent neural network and do lots of steps internally. What turns out that text works really well. And so again, these are some very old slides. This is actually was my first project when I joined OpenAI, and then it's going to show you like a little exploration of what models could do, but just asking them to think when they were not ever trained to think. And this is one of the pieces that gave us confidence to scale things up. And so, okay, again, these are the old slides. The pitch was, what if we just asked them all to think about it? And so I had a bunch of examples. We're going to go through them. Again, they're very silly for today's standards, but it's good to see how far we went in such a short amount of time and where we used to be at the time. So at the time, you could ask GPT-3 a simple math problem. There are 29 bags of potatoes, and then 17 more, and there's plenty of bags, and the model would say that there's 46 kilos of potatoes, which is obviously completely wrong. And so one of the first exploration was to just add, let's think about it before getting the answer. And then the thing you would get is you wouldn't get an answer right away. The model would start to output some extra text, but then eventually you would get the right answer. And of course, not all the time, but at least sometimes compared to never. Okay, so then we kept going. A bunch of questions. I have a clarinet, a piano, a dog. How many musical instruments do I have? Model said 1. That's, of course, wrong. Clarinet and pianos are both instruments. You would break it down, think about it step by step, and then you would get, a dog is a musical, it's not a musical instrument. A clarinet is a musical instrument, but a piano is not, so it's still 1. And so then you would try to think, okay, well, if this model only thought a little longer, and so you add, well, also break it down step by step. And then say, well, first we have a dog. Dog is not a musical instrument, and then if you have piano as a musical instrument, a clarinet is, and so then you get the right answer. Here's one more example. There's a chair, a lamp, an oven, lots of things, and then the model would say 20, and the answer is 14. Back in the days, you could check what was the probability of getting the answer 14 out of the model, and the probability was 2%. So basically almost never. Then again, you add, let's think about it, break it down step by step, and then you would get this long list when the model counts one by one, and somehow you get a better answer. Okay, so this intuition seems good, then how do we make it quantitative? And this was one of the first plots about what happens if we get this model to think for longer. And so these are the last 2 plots I have to show you. This is just if you do this trick of asking the model, well, think step by step, and then think step by step, break it down, and keep adding sentences to say, look, I really want you to do all the work and show all your work and make sure there are no mistakes. And so we went from this model that could barely solve problems to, by just adding things, get to models that could solve more and more problems by thinking longer. And so the last plot I want to add is this one, which should have gone with the other one. And this is the average length of the solutions generated by the model when you asked it to solve a problem. And so again, at the beginning, you would get almost nothing if you just asked to solve. And then as you kept adding instruction, and you had to use this trick of saying first, comma, so the model wouldn't, again, just try to answer and get into this mindset of, okay, it's going to be a long list of things I need to do. So first, this something, then there must be a second and a third, and so let's try to output a lot of text. And so as the amount of text the model was outputting was increasing, then the accuracy of the model was going up. And so since then, lots of other people worked on this. We did a big project, and then lots of other components we can't talk about yet, but very humble beginnings, one of many, and I thought it was interesting maybe for you guys to see this in the midst of this talks about the future. All right, that's all. Thank you.
Thank you, GB. All right, next up, we have Aditya Grover with Inception Labs.
All right. Hello, everyone. My name is Aditya. I'm one of the co-founders and the CTO at Inception. And today what I'm going to talk about is actually going to take a lot of elements from what we just heard in the previous talks into defining what I believe will be the new foundation for generative AI, something that's extremely fast and efficient and builds on ideas from diffusion. So to take a trip down memory lane, I think there have been a few fundamental advances that have defined what AI looks today and what I believe AI is going to look like in the future. And at the heart of all of these advances is the idea that parallelization is a fundamental concept for computer science, fundamental concept for AI, and fundamental belief that will also guide towards the future. So if you think about the late 90s, the idea that we finally had hardware which could execute a very simple but basic operation called matrix multiplication in parallel was turned out to be the defining moment for what we see in today's generative AI world. A few years later, we realized that there's also something that could be done in terms of architectures when we had the transformer itself as the fundamental neural architecture which could be used to train AI models in parallel. And this was how, from the world of RNNs and LSTMs, which were fundamentally bottlenecked by how much they could learn with every dollar of compute spent, we went into a new era where we could train massive language models using the transformer architecture. Within all of this, we also have started thinking about how these ideas could then also be applied on the algorithm side. And that's where there were fundamental advances in vision that continue to be the state of the art today. So we have diffusion, which replaced what was at that time the dominant paradigm based on GANs to become the dominant way in which we generate images and videos extremely efficiently and with very high fidelity. Now, this was something which works extremely well even today, but so far, most of the state-of-the-art demonstrations of diffusion have been limited to images, but there has been a recent wave of work now taking in the same ideas and applying it to the field of text. Now, why is text hard? So to understand why text is very different from images, it simply boils down to the fact that the notion of diffusion was invented for continuous modalities. So if you think about modalities such as images, there's a very natural notion of what it means to add noise and then a good mathematical theory to what it means to do a principal denoising of it. Text, on the other hand, happens to be discrete, which makes it fundamentally very hard to think about what are good notions of noising and denoising which can be trained at scale. So at inception, what we've been doing is trying to build a new generation of language models which apply this idea to long-range text sequences. And how it basically works is that instead of generating tokens sequentially, one token at a time, which is what practically all language models of today do, that's the autoregressive paradigm that you see at the bottom, what we are now doing is we are coming up with a way in which you can denoise text. So you could start with something that's extremely gibberish and then pass it through a neural network. This can be any architecture. We use transformers. And through this transformer neural network, you're now training it to fix the noise in its input. So that's how you can then find structure within text and generate something extremely coherent in much shorter amount of time, because now you're trying to predict all the denoise tokens in parallel. So this is tracing down the history of text diffusion. So in 2019 is when denoising diffusion started taking off for images. So this was the time when companies like Midjourney, as well as from other labs, including Google, OpenAI, were coming up with very large-scale demonstrations of how diffusion can generate extremely high-quality images. It took many years and work of the entire research community to come up with ideas which eventually led us to the point where there was a breakthrough from one of my co-founders' lab where we were able to then design a diffusion model for text that achieved parity with GPT-2. Now, of course, in 2024, GPT-2 was no longer the bar for success in language, and that's when we decided to form this company called Inception and really take this idea at scale. A few months later, we launched Mercury, which is the first commercial scale diffusion language model, and it was able to generate text at very good scales and do a lot of good tasks, including code editing, code generation, mathematical problem solving, common sense at scale, and extremely fast. And this, of course, also caught the attention of a lot of notable folks in the field, both in academia and industry. Very quickly, a few months later, many different labs from Google to NVIDIA to Alibaba followed up with their own efforts in building diffusion LLMs. And earlier this year, we launched the second iteration of our model, Mercury 2, which now also had capabilities to do reasoning. And unlike other LLMs, diffusion reasoning looks very different from how it works for autoregressive LLMs. And the best way to illustrate that is through this chart. So this is a chart from artificial analysis, which is comparing Mercury with the state-of-the-art LLMs for the speed-optimized regime from different labs. So on the x-axis, you see the speed as measured by tokens per second, so higher is better. And on the y-axis, you're looking at some kind of quality index. In this case, it's the one that's defined by artificial analysis across a wide range of agentic benchmarks. And what you see here is that Mercury gets you similar quality as you would see for models of similar size. So if you think about your Claude Haikus, you think about the GPT-5 minis. So these are all the speed-optimized models from Frontier Labs. And it gets you similar quality while being much, much faster. And that's because it's denoising tokens in parallel. It's breaking away from the paradigm of generating tokens sequentially. So this has now been commercialized as well. So we provide a drop-in replacement for existing language models. And there's a lot of different applications that are being built on top of these models. So a lot of them are ones where speed is extremely critical, along with also concerns of cost. And all of this has to be done at a desired level of quality. So some of the domains where we are seeing a lot of success is in voice, in coding, and search. Just to show you a few case studies of how this has come to the real world. So for voice and support agents, what you can see is that what you really care about is not just intelligence alone. You care about intelligence as well as the time for response. So in particular, the time to first token is extremely important for any kind of customer support, voice kind of applications. And for these kinds of applications, if you look at these charts, what it's really showing is that Mercury defines a different kind of frontier where it gets you extremely good intelligence at a very small time to first token. In fact, compared to even non-reasoning models, such as GPT 4.1, which is in production at most of the voice companies, Mercury 2 can do reasoning and still be faster than a GPT model. So that's what speed buys you, where you can actually deploy reasoning models at the speed or even better than non-reasoning models. So extremely good quality at a fraction of the speed. Now, one thing also notable in this is all of our deployments are on NVIDIA hardware. So this is coming purely because of the fact that we have trained these models using diffusion, and we are generating tokens in parallel. So any of these complementary advantages, such as those that could arise from modern hardware like Cerebras and Grok, could pair up potentially very well with having a diffusion model for text on top of it. This is another case study for search. In this case, you not only care about speed, you also care about cost. So these two plots are showing how accuracy varies with each of these factors. And again, you see a similar kind of trend where the models that you can actually deploy in production should have a good combination of all three, and Mercury strikes a really good balance in this space as well. Coding is another space. Of course, I can't imagine my life now without using coding agents. And what you see with coding agents is, again, that you might have a primary agent that's extremely verbose or might use a lot of tokens, but that's not always what you need in order to drive down the token economics towards something that's sustainable. So companies like Augment Code are using Mercury in conjunction with some of the more heavyweight models like Opus to get a very good balance, reduce latency as well as costs here. And I would end with this slide where if you think about the frontier of intelligence, we have reached a point where we have extremely good intelligence for a lot of applications. But now what's really important is, as we build value for everyone around us, is to think about the new currency of intelligence per watt. And diffusion LLMs seem like a really good bet to redefining that frontier. Thank you.
All right, thank you, Aditya. Next up, we have a workshop from Daytona, and it's going to be an hour session, and after that's going to be lunch. So welcome up, Daytona.
Hey everyone, I'm Mohammed. I'm a developer relations engineer at Daytona. At Daytona, for those of you who don't know, we build infrastructure for running agents and their workloads. So we basically provide computers you can create through an API and compose, choose their operating system, choose however many CPUs, how much RAM, disk, et cetera. And the two primary use cases why people use us are for running agents in the background or on the cloud, and also for reinforcement learning. And so to kind of understand that is when you train an agent, the model learns by doing the task, and coding agents or computer use agents, they need a compute environment to perform those tasks. And so our infrastructure happens to be pretty well suited for that use case. And yeah, the talk or the workshop is kind of about how we came to this point, like how exactly we went from chatbots to today's agents. A few years ago, the state of the art was like an LLM that you sort of treated as like a question and answer assistant. It would sometimes be helpful, but it couldn't actually do anything. But now they can act, and so yeah, that's going to be the presentation essentially. So the first half, I'm going to be kind of going over the history, how we got to the current point, and the second half, my colleague Luve is going to be going over kind of like where Daytona fits into this and some of the more modern techniques that our infrastructure shines in. Cool. So I think everyone is probably somewhat familiar with this, like the classic terminal agent. This is an example of Kimi K3. You give it a prompt to fix a bug, implement a feature, and it starts running a bunch of commands, writing files, etc. Now, I want you to consider, let me see if I can go to the next slide. This is the same model, given the same tools, all else equal, or not the same model, same harness, same tools, but it's GPT-2. So this is a model from 7 years ago. And so when you send the same prompt, it just breaks. It doesn't know what to do. And yeah, that's kind of the main point, is understanding, how the difference between these two slides. And kind of I guess the short answer is reinforcement learning. But what's interesting is there was sort of two developments happening at the same time. One is, people kind of, reinforcement learning is not a new thing. It's been a thing for multiple decades. Really just what changes kind of the model behind it and what gets rewarded. And so this is sort of a timeline of what I'll be talking about. And it's helpful to also understand how an LLM works, and to kind of get a better understanding later on when we talk about what gets rewarded, how does a model actually learn, what does learning really mean? And so this is kind of the most basic example of an LLM. So you have it's writing a sentence, and the next token is calculated by sampling from a probability distribution. And so at each step, you have a certain amount of tokens to choose from. Some are more likely, some are less likely. Sometimes the least likely one gets picked. And so yeah, I think this architecture is not probably super new to most people, but yeah, that's sort of the motivation behind, or the background behind like what pre-training is. So you want to make the model output whatever you're training it on. So if you're training it to be a helpful assistant, or maybe it's just like completing a Wikipedia page entry, you kind of let the model, output what it thinks is the most likely next token, and then grade it based on the actual ground truth. So this is sort of a example of, let's see, sort of a zooming in on how it works. So you have, at the top is the ground truth of what the model is being graded on, and then the bottom is each token that it outputted. And so you can kind of go through each step. So like right now, we'll just look at this token at the end, crew. We see that like so when the model was, prior to this step where its weights got updated, the probability at the time was 0.61%, and then, when the loss gets calculated, which the loss is just the negative log probability, that step gets applied to its weights, and then all the kind of previous tokens, the weights get updated to be to match the ground truth more often. And so you can kind of go, you can see each one. It's a little bit of a cluttered slide. Hopefully you guys can read it, but yeah, you can see exactly how the weights and the probabilities got updated. And so, after you kind of had like models that just completed a sentence, and a pattern that kind of emerged from that is you could show it a pattern where, let's say you have like, for example, this is sort of a toy pattern, but I guess a more realistic example would be if you had a list of Python functions and then you wanted it to fill in like the fourth one, then it would know somehow that it would learn from the 3 patterns that you showed it in the input, and then like pretty accurately predict what the fourth one would look like based on that pattern that you showed it. And that's all just in the prompts. That didn't require any like teaching the model to do that. It just saw the pattern and kind of learned. And so like the point is like nobody really, this is kind of a emergent property that fell out. Like no one kind of like built that pattern into the weights. It just fell out of next word prediction. And we noticed that like if you take that same concept and you just apply it to a larger model, it gets a lot better at following those patterns. And there was this kind of a few years ago, this paper about thinking step by step, and basically you can kind of see, and some of you might remember how when you would prompt like GPT and you explicitly told it to kind of think more systematically, think more carefully, it got the right answer. It would be able to kind of quote unquote reason about the problem and arrive at the right answer more often than not. And so the way that I was kind of showing up until this point, mostly just models that completed the sentence, whatever you gave it as input. But I think most people remember models behaving as assistants. But in order for it to get to that point, it kind of had to learn the pattern of being an assistant. And so the way that happened was just you show it a bunch of question and answer samples, and it learns that pattern. It kind of understands, okay, depending on the question, you want to be like a helpful assistant to the user. And so that was another kind of like major shift. And yeah, this is an example of a query you might ask one of those assistant models. Like the answer would be something that is hopefully helpful. I don't know if we'll be able to. Yeah, this is kind of the same concept earlier where you kind of like update the weights so that the model learns how to behave more like an assistant more often. Sorry. Yeah, I think these slides are kind of repeating that concept more or less. And so I guess some limitation was reached, or that's kind of like fundamentally limited in that like you can teach it to imitate patterns, but really like if you, let's say you had a data set from a math textbook and all you did was kind of like reward it based on whatever tokens would lead to the final answer. That's in a way like prescribing how the model should behave to get to the answer, and this will sort of make sense later on. It's limited in that we don't know exactly like, I guess, what the best way is to arrive at that answer inherently, and so what kind of motivates like reinforcement learning is that all you do is, reward the final answer, and then hopefully, which it did turn out to be true, the model would the reasoning from the model would emerge from that point, as opposed to, having humans kind of like tell it how to reason. And yeah, this is kind of a basic diagram of reinforcement learning. You have your agent, it acts on an environment and then receives a reward. And so one thing before even getting to reasoning, I think there was this like concept of human feedback. Which response would you prefer to hear when you receive that response? You might remember using GPT and like it giving two different responses. I'm not sure if they still do this, but yeah, you kind of choose what you prefer. And then based on that, a reward model gets trained that kind of makes the underlying LLM more aligned to whatever humans prefer. And so this is getting a little bit, I think I'll probably have to skip some of these slides for the sake of time, but this is the objective that is optimized when doing reinforcement learning with human feedback. And so yeah, it's sort of an example of what I've been talking about. Let's get these. And so, yeah, going back to what I was saying earlier, if we know that reasoning helps, then why do we try to teach it to imitate a written solution? Why not just reward it based on the final answer and then see kind of what comes out of that? So that's where reinforcement learning with verifiable rewards came, or kind of showed that a model can, without even being told how to arrive at the final answer necessarily, if it just gets rewarded based on its final answer, it'll learn to reason better, and that'll transfer to other problems. And so this is kind of a fast-forwarded output of DeepSeek R1. And so like, instead of, going back and seeing, did it reason correctly? Did every token up until the final answer match what was in my data set? All we do is check the final answer. And so, one problem that emerges from that is if you have a really long reasoning chain and it does get the final answer or it gets it incorrect, how do you know which tokens in that trajectory like earn that reward? Maybe the model is going down a path that was reasonable, and later on, let's say like a few thousand tokens in, it took a bad path. Maybe you don't want to penalize the quote unquote good tokens. And like I guess the answer to that at the time was having a critic model, which kind of like guesses like, okay, is this token that was predicted, better than expected? As in, was it already very likely to, output this token? Because in that case, it probably doesn't deserve to be rewarded as highly as other unlikely tokens. Hopefully that makes a little bit sense. But that sort of required like, training in tandem another model. But this other, the solution to that at the time that kind of like changed things and made things a lot more efficient than having to, train another model is this other policy optimization, group relative policy optimization. So instead of like doing one sample and then grading every token in that trajectory, you sample a group and then you sort of use the having multiple rollouts as a proxy to like which rewards are more deserving of credit. So as an example, let's say you have on one task 4 rollouts or 4 attempts at that task, and like most of them pass, but one of them failed. So that means like the one that failed was pretty unexpected or like unlikely. And so we really, really want to make sure those tokens are penalized harder than the other ones are rewarded, because it's already pretty likely to get the correct answer. And if we don't really take care of this like relative reward, if we reward everything equally, then you can imagine like the model will converge towards one kind of way of doing things. So that's kind of the motivation behind like why we want to assign credit particularly. And this is so this is sort of an example of what I showed in the previous slide. So like we have 4 trajectories here. One of them received, here they go. 2 of them received the low reward, 2 received the high reward. And I'll just go quickly over like what it might look like. So, you calculate the advantage based on the mean reward, and then use that to calculate the loss, and then that sort of updates all the weights. And yeah. And so like, we still haven't really answered like how did we get to the point where models could actually do things, right? For a model to write code, ideally it could test that code. That way, like, at least you know that it failed before, pasting that into your editor. And so this is kind of where the concept of tool calling came, where a model can output certain tokens, and those will get parsed as kind of almost like a function execution, essentially. You look at I think I have an example on the next slide, actually, that'll just make things a little bit clearer. No, never mind. So yeah, essentially you look at special tokens that the model outputs for, depending on how you might want to train it, you teach it to output tool calls in a certain format, and then it learns to, you sort of like reward it to output in the format, and then reward it to use that more often when solving any problems it might be given. And then it learns to, when it thinks it needs to call a tool, it outputs those tokens, wraps whatever it needs to run. So in this case, this model I'm using wanted to run this command, and so there's a parser not shown here that waits for an output that looks like that from a model that's wrapped around special tokens. And when it sees that, yeah, it kind of executes that in an environment. But one tool call isn't really an agent. An agent is, like we know them today, they keep on acting until and observing until the task is done or until it thinks it's done. And this is sort of like sort of the evolution that it's a little bit outdated, not super outdated, but yeah, you guys probably remember at first it was like, GitHub Copilot, and then the agent actually like lived in your editor, and now like we use terminal agents, or some people might still use editors or other UIs, but yeah. And so like the point is that the environment that we think of like when we think of reinforcement learning became a computer, because these agents, coding agents, they need to call tools that file editing tool, code execution tool has to be executed in some compute environment. And so like training an agent now, you have to deal, this was the case previously, but now it's like at a larger scale, you sort of like have to deal a lot with cloud infrastructure and handling that. That's sort of, like I said earlier, yeah, one of the reasons why people use Daytona for reinforcement learning. And actually, to make that more concrete, my teammate Luger is going to come up and kind of show you guys some, go over how our infrastructure fits in, what role we play, and some modern techniques and examples that hopefully is helpful in understanding like now that you kind of got a grasp of the history, like what does it actually look like today? So yeah, thank you all for listening. Again, apologies for the technical difficulties earlier, but yeah, hope you guys enjoyed.
Yeah, thanks, Mohammed. So yeah, I'm going to like show some, specific examples of, RL training runs which use a sandbox, and yeah, also like examine. Okay, so like what does modern reinforcement learning look like? Like there's a lot of we don't like necessarily know. We don't really know like how the OpenAI models that have solved all these open mathematical problems have been trained, but we do know like a lot about at least Chinese models, Kimi, K2, GLM, and then also into West the Composer 2, which is also based on Kimi. But yeah, so like we do know some things about how the modern RL is done. And one thing that we do know is that it's done in sandboxes, which means every agent gets an isolated computer in which it does a certain task, and then it's graded based on some verifiable criterion. I mean, there's also like more things that come to it, and we're going to see some of them. But overall, yeah, that's kind of the standard right now, which is just rollouts in their sandboxes. I mean, that's also kind of a side effect of nowadays coding being the biggest application of these models. So yeah, we're gonna see like a specific training run on Qwen 3 8 billion. Just doing some standard Python things in a terminal basically, and we're just gonna like examine what happened during that run. Some things might generalize like big training runs, some might not, but yeah. And yeah, for this example, we're gonna be using Sky RL for like the trainer part, and Harbor for the environment and the rollout part, and the environment is going to be Daytona sandboxes basically. But I mean, it could be run in any kind of sandbox. So yeah, and I mean, this kind of points to one thing that is like maybe worth mentioning, which is that in RL, you basically have two parts. One is the part that generates your rollouts, and the other is the trainer, which updates the weights. And nowadays, usually you have like different libraries dealing with each of them, and then you have like some different sandboxes as substrate. So yeah, that's one kind of distinction worth keeping in mind. So yeah, this is one. This is kind of the case study of a reinforcement learning run. It's 28 billion. Run on 8 H100s over 4 hours, starting with about 30% accuracy, or rather the 0.3 reward, but that is basically because this is the binary reward that corresponds to the accuracy on solving these coding tasks. 4 hours over which 1,440 rollouts happened. It tried to solve that many problems, of course, some of them repeating. So yeah, we're gonna just hop into this different slide. We're basically gonna see that training run sped up like 60 times here. So here we can see the GPU utilization, which is gonna be a bit jumpy. In some super optimized setups, you wouldn't have it super jumpy, but here there is some downtime as the sandboxes start up and as the episodes wind down, basically. But yeah, basically you can see, so this is going at 60 times, so each second represents 1 second of the training run. Here you can see, so each step involves 8 tasks, 4 rollouts for each of those tasks. Some of them fail, some of them succeed. Sandboxes are getting created all the time. In each step, 32 of them, then toned down. The reward is slowly climbing up over this time. You can also see the breakdown here of okay, so each individual step in this training run, how much does each of its subcomponents take? And usually it is in RL training runs that most of the time you spend on actual rollout, so on the model acting, generating its turns, etc. But then you also have the turn where you're doing the backwards pass, which can also be kind of a non-trivial part of it. And you also have the weight syncing. So after you've updated the weights, you want to so in your trainer part, you want your rollout generator parts to get new weights or other new policy. Yeah, this is an example of a completely synchronous reinforcement learning run. So that you just do one step, you update the weights, you update the policy or update the weights, and then you do the next step, the future rollouts with completely new weights updated. So this is one of the things that's done a bit differently in the name of efficiency nowadays. There's a few optimizations we are going to see and that are used in these big training runs, such as Kimi, K3, and GLM runs. But yeah, this is wrapping up slowly. This training run, sped up 60 times. But yeah, the kind of the thing to notice here is just there's this whole cycle. Some of it involves the weight, some of it is related to sandboxes, which spawn for individual rollouts in each step. So yeah, one kind of thing that I think it's kind of interesting about reinforcement learning is that in some ways it can be more interpretable than pre-training, because usually the volume of data is smaller, and you can just look at the trajectories and see what the model found that worked. Just kind of analyze them. There's a much smaller amount of data, basically. So in this previous run, So model went from, like, let's say 30% success to approximately 60% success. But kind of an interesting thing is just to notice what it kind of learned. It didn't learn some new insights about algorithms and such things, but it just learned to format, what it wrote better. So it didn't do like double quoting inside double quotes when it wrote things to a Python file, to a text file. It didn't, one of the things that tripped it up, so it happened in about a quarter of rollouts at the start, was it would output the literal new line character rather than the actual new line. And so like those are the things that the model kind of actually learned during this training run. And it kind of connects to that whole debate, like whether RL actually teaches the model new things, or does it just like reinforce things that were taught to it during pre-training? And I mean, at least in this example, we could just say that the model mostly learned to like deal with the format of things like that, to deal with it with harness rather than learning some like new algorithmic things. So yeah, in each rollout, you basically only train on the agent tokens. You have also like tool results, et cetera, et cetera. So I mean, this is a bit of a technical thing about on which tokens to actually train. But yeah, let's go into the meat of like, okay, so what happened during like some of these big recent training runs? Yeah, K-tree, there's like a lot of interesting details in their tech report. And they do state exactly that they used 51 million sandboxes. They also like used micro VMs for it. And in particular, there's like one interesting feature of like micro VMs. So they like used the pause feature a lot because Kimi like tends to think a lot between turns. And so basically what this means is that you can like pause the sandbox between the turns while it's doing the thinking, so it's not using up the compute resources. So yeah, there's like a lot of interesting details. One of them is like how did they prepare the model to like be ready for any harness that could be thrown at it. Like, so it works at Kimi's Kimi code, but it also works at Claude Code, Codex, et cetera. And what they did was like a dynamic harness where they like basically have a config which turns off and on various like aspects of a harness, like system prompts, subagents, memories, skills, et cetera. And like doing that, they kind of like use this as a data augmentation axis. So they like get data augmentation, they prepare the model for like all the current harnesses, but also like probably some future ones because it's trained on many permutations of features of the harness. Yeah, that's kind of an interesting contrast with the Composer 2 approach. Because Composer 2, which is Cursor's model, they basically like specifically trained it on the harness for Cursor. So like Kimi's approach is basically diversity, harness diversity, and achieving robustness to anything you could throw at it, while the Composer 2 approach from Cursor was like, let's get this model really ready for Cursor. So that is kind of quite a different approach to preparing the model for its agentic work. So yeah, here's like a couple of other kind of interesting aspects of Kimi-K training. I mean, this is about how they taught it different reasoning levels. They were basically just, for a given reasoning level, give some token budget, which is also like problem dependent, And then also like just if the model went over the token budget, they would just just give it -1 reward, irregardless of whether it was right actually. And yeah, so like the final model actually was composed of 9 reinforcement learning runs, which are then, then on policy distilled onto the final model. And so they did like 9 models. So the matrix, 1 model for each reasoning level, low, high, and max. But also they had like general model, like general conversations, the agentic model, and a coding model. So there's like 9 separate reinforcement learning runs, and then all of them got distilled into the final model. So, I mean, they did verifiably did some distillation. We just don't know if it was also on some other models, but this is like kind of approach of training expert models and then distilling them onto your kind of main model. So yeah, the on-policy distillation is kind of a technique that's nowadays used a lot, and it kind of composes nicely with reinforcement learning in general. So basically, as in this Kimi K3 example, they had like, let's say some, coding expert model. And then they would generate rollouts with their, generalist model, which is not to be confused with the general model in the previous slide, but just like their final model. They would generate rollouts with it, and they would score its tokens with the expert model. And that way they would like, they would distill all these models, kind of impart part of their wisdom into the final model. And this is like a pretty versatile technique. You need to access to the model so you can get its full log probes for every token. But yeah, if you do, it's pretty powerful for distilling or going from a teacher to a student model. And yeah, another kind of like interesting thing nowadays is that you need like a lot of environments, and that's like a pretty big industry nowadays. But Kimi K3 and GLM at least do share some details about how they actually make synthetic environments with their agents. So like there's like a lot of variety there, and Kimi K3 actually has like this big directed acyclic graph of like the internet where like they try to like cover every area with some synthetic environment. And just, the kind of the environments is a new form of data, so to say. So previously we would like try to increase your data set as much as you could. Nowadays, like there's a decent amount of pre-training data on the internet, but there's like not that many environments. And so that environments are currently actually valuable part of the kind of the data stack, and then you want to employ your models into building better and better environments. So yeah, one other thing that's like pretty prominent with the current models is like the prevalence of reward hacking, which is basically a model does something that kind of on the paper satisfies your reward, satisfy your verifier, but it doesn't like actually correspond to the actual thing that was supposed to be done. So there's like this very famous illustration of reward hacking from 2016 from OpenAI, from like a very simplistic game where the model was, it was supposed to learn this game, but it just like learn to spin in a circle and collect these kind of score packets. Yeah, so what one says with LLMs is, something like this, but just a lot more sophisticated because, your kind of policy is actually, an intelligent agent, which is, actually trying to, and now, as we know, actually, reward hacking has like kind of become literal. It has, has literally become hacking nowadays, at least in some cases. So yeah, there's like Kimi and GLM at least talk a lot about these specific measures that they took. So for various kind of environments, they do different interventions that prevent supposed to prevent or ameliorate reward hacking. And like, for example, writing kernels is like one of the environments in which there's like a lot of ways to hack. So there's like a lot of effort needed to expend to make sure that your reward is actually a real one, and then not a kind of like just a quirk of your verifier, so to say. So yeah, what is actually, so I talked a little bit about this before on that, like live, rather sped up run. So where does the, in a single step in reinforcement learning, where does the time go? And I mean, it's mostly into rollouts because models take a lot of time to think. They possibly execute actions which take a long time to execute. And so that's kind of the part that costs you the most. And in particular, in like the fully synchronous reinforcement learning, you're constrained by your longest rollout. So that you're just waiting on all the episodes to finish, so you can go to your backwards pass, to your weight syncing part. And yeah, so you're waiting possibly a long time for a single rollout to finish. And that's actually one thing that's not much time, so I'm gonna speed through a couple of these slides. But basically, you can just try to generate as many rollouts as you can, not wait for some specific ones to finish, and just wait for a certain number of them to finish, and then immediately update your policy, update your weights. So that's the asynchronous reinforcement learning, and it's quite popular nowadays for maximizing throughput. But yeah, there are like some, you get rollouts generated by stale policy, and that's kind of it. Both breaks some of the like the theoretical assumptions of reinforcement learning algorithms, but also it just makes the whole thing more unstable, and reinforcement learning is like already kind of notoriously unstable. So yeah, you kind of do that as a sort of a trick. And Kimi K3 actually did like something between synchronous and asynchronous reinforcement learning, which is that they collected like a certain amount of rollouts. They would pause, but they would like then pause their rollouts for the next weight sync. So they would like it's a bit of a less extreme version of the asynchronous reinforcement learning. Fully asynchronous, the policy moves on, and then just you get a lot of staleness of it, which can hurt you in some non-trivial ways during the training process. So that's more or less it. So we've seen that, the kind of like the API of modern reinforcement learning is pretty standardized now. You have, your trainer, your rollout generator, and you have somewhere where your sandboxes are run. And that's what we've seen in Daytona, like a lot of demand for sandboxes specifically in reinforcement learning. So that's it. There's like a repo which you can find if you wanna like look at the code that generated some of these things in the presentation. And that's it. Thank you all.
All right, thank you, Daytona. We have lunchtime now. Outside in Lower Sprawl Plaza, there'll be lunch. And then at the first floor, we have our posters and sponsors. So we'll be back at 1:30, so enjoy lunch. Thank you.